So these are two kinds of special matrices that we'll be dealing with. The first one is a zero matrix. So a zero matrix is nothing but a matrix where all the elements enclosed are zeros, while an identity matrix is something special. So basically the elements on the diagonal, as you can see over here, will be ones, and all the other elements in these triangles on the sides will be zeros. So identity matrix play a particularly important role in several matrix operations. So generally, if you take a very technical linear algebra course, you'll get rigorous definitions for each and every one of these. But for the sake of ease and convenience, I'm going to use rather simple terminology to, explain this concept. Think that you're just dealing with normal numbers for a second. So assuming that all matrices become normal numbers, the identity matrix is just your 1 and zero matrix is just your 0. Okay, so in most of your calculations, just this assumption usually helps you do your stuff smooth, particularly when you're dealing with calculations in MATLAB. But I really do suggest that you can potentially go take a linear algebra course from if you want more detailed information regarding that. Moving forward, let's actually talk about when we can say that two matrices are equal. Well, in the cases of numbers, this is quite something which is very easy. Just you might be familiar with what the concept of one number being equal to another number is. But in terms of speaking in terms of matrices, we'll be obliged to the fact that each and every element inside a matrix should be equal to the other corresponding element in the other matrix in order for both the matrices to be equal. So how this has been demonstrated in this presentation is that we see that there are letters in the second matrix A, B, C, D, E, F, G, H, I, and below we have demonstrated how these two might be possibly equal. That is, this element A must be equal to 1, B must be equal to 2, C must be equal to 4, and so on. So that is the condition for equality, and I hope that's clear to you. Let's move on to addition then. Again, quite simple. Addition, is just element-wise addition. So the first element here will be added with the first element over here. As you can see, 1 minus 1 gives you 0, and 2 plus 3 gives you 5. So again, that's something which is very simple. Just do it element-wise, and you should be good. Yep. So addition of matrices, again, these have properties just as you would have studied your basic properties for numbers. Well, you need not necessarily know all this stuff for MATLAB and Octave, but this is just helpful for generic linear algebra. The commutative property, of course, which is just that A plus B equal to B plus A during addition of matrices, and then the associative property where you do A plus within brackets B plus C is equal to within brackets A plus B plus C outside. Fine. So again, you come to the additive identity, or what we call as addition of the zero matrix property. This is just that when you add a matrix with numbers with just a normal matrix with a zero matrix, then you're gonna get A again. So I hope that's understandable. Okay, proceeding to the next concept. Let's talk about multiplying a matrix with a scalar. Again, we're talking about an element-wise operation where if you're going to multiply a matrix with a scalar, then you're just going to be multiplying it with all the elements inside that matrix. For instance, if you take this matrix A that's been given here, we're talking about multiplying the constant C with each and every element inside to give the resultant matrix, as you might see here. So this is just a very special case, a very obvious one, in fact. Just that you can get the negative of a matrix just as you can get the negatives of numbers by multiplying it with -1. Not a big deal of something, just something you need to keep in mind that matrices also have negatives. So also subtraction, I hope you would have obviously understood that it's just element-wise subtraction, as you might have observed from this slide itself. Or to be rather technical and rigorous in definition, it's just A added with the product of -1 and B. I hope it's all obvious just from the way they've portrayed it here, so I'm not going to go more into detailing this information. Then let's start up with some special operations that we can perform upon matrices. So the first one is called transposing a matrix. So this can be denoted in two ways. Number one is that you can denote it by raising a to the power of t, or actually that's not a, it's just it's called a transpose. So a raised to the power t, or superscript t, is the notation for it. Or you can also represent it using an a dash, or a dash on top of a, which will be the notation we'll be using in MATLAB. I'll show you that later. So anyways, what is a transpose? It's just that you're going to be swapping the rows and the columns. In other words, your first row will become your first column, as you see here. Your first column will become your first row instead, and that's how it just works. So when you're asked to do a transpose, just swap the rows for the columns and the columns for the rows. I believe that's again something which is quite easy. Also, we need to understand that let me first deal with the concept of a square matrix here. So if both the dimensions, that is the row dimension as well as the column dimension, is the same, then a matrix is called a square matrix. And for these square matrices, we have a condition called symmetry. So symmetry means that if the transpose of a matrix is going to be equal to the matrix itself, then that matrix will be called symmetric. So, of course, you can try out some matrices doing that, swapping elements around, swapping the rows for the column, and you can play around with this concept of symmetry. Symmetric matrices have certain special properties in linear algebra, which you might not necessarily need for this course, but if there is anything related to that, I'll certainly deal with it and make sure that you get to learn that too. Dot products of two vectors. All right, so this is where we're actually coming into the actual operations that we'll be dealing with on a large scale in MATLAB and Octave. So as you see, what I mean by dot product of two vectors is that I'm going to take the sum of products of the respective elements. So in this case, we are taking the sum of products of, as you see, A1, B1 is your first product, A2, B2 is your first product, A3, B3 is your first product, and you're just going to summate all of them. You see here that it's A transpose B2. Well, rather than explaining scalar dot product, I'll first explain the concept of matrix multiplication in detail to you, and then this part of it might be more obviously understandable if I do that, I guess. There is this one special condition that we must satisfy if we are to do matrix multiplication, and that is that these two dimensions should be matching. So let's say we have a matrix M cross R, and the second matrix is R cross N. Okay, so the number of columns in A should be equal to the number of rows in B. And only if this situation occurs, then matrix multiplication is possible, and otherwise it is not. And so the eventual dimension of the product, which is AB, will be M cross N. So that is something to be noted, and understand that only if this condition is satisfied, then things are going to work out with matrix multiplication. So that being said, let's move on to actually learn how to perform these matrix multiplication operations. Okay, so get straight to matrices A and B. So you see that A is a 3 by 3 matrix, while B is a 3 by 2 matrix. So as we see, the number of columns in A is obviously equal to the number of rows in B, which is 3. So first, let's get an idea of what the dimension of our resultant matrix is going to be. So we're going to take the number of rows in R and the number of columns in B. So that's going to be 3 by 2. So 3 by 2 is the size of the resultant matrix. Let's say that's C. So what are we doing here? So you see that we're taking the first row of A, and then we are going to multiply it with the first column of C. I'm sorry, we're not multiplying it, we're taking the sum of products. In other words, I'm going to multiply this 1 by this minus 1, this 2 by this minus 3, this 4 by this 1. I'm going to summate all that, and the resultant will be my first element here. So then what will be the second element? For that, I'll be taking the second column of B and the first row of A, and then this 1 into this 3, this 2 into this 1, and this 4 into this 0. Again, I'll summate all that stuff, and that will be my second element. All right. So that is pretty much how matrix multiplication works. To give you a further instance, let me also go to the next row. Let's say I want the element in this position. Let's say I want this 10. What I'll be doing is I'll be multiplying this row with the elements of this column. So that will be minus 3 into minus 1 plus minus 3 into 0 plus 7. And then I'll place it over here, and that's 10. So that's how we build these multiplied products. I hope that might, if you don't have familiarity a lot with matrices and vectors, well, that might be tricky for the first time. But then again, I suggest that you only need to know the pre-existing condition, which I told you, to actually really understand this stuff. That the resultant dimension, all the other stuff, all the other calculations and stuff, MATLAB is going to take care of that for you. So if you don't have a lot of clarity about it, don't worry about it. But if you're really keen on understanding this stuff, well, I really do suggest that look up Khan Academy or there are some really good, awesome resources that will teach you how to do this in detail. So again, we have some properties related to multiplication of matrices. So, well, the first one is that it's non-commutative, which means that AB is not equal to BA in general. All right. So what that means is that there are some cases where AB might be equal to BA, but those are exceptions. In general, AB is mostly not equal to BA. All right. So also, just because AB exists does not mean that BA will exist. So again, the existence of the product matrix depends completely upon the dimensions factor, because number of columns in the first matrix should be equal to number of rows in the second matrix, and given that is satisfied, only then will you actually have a product matrix. Otherwise you won't. If you really want to start up with learning the language, please do make sure to check our first lecture notes or the first lecture video. I hope you'll get a good introduction to what MATLAB and Octave are, and I hope you'll have a smooth learning experience from there. So given that there might not be any questions at this point of time, I hope to continue at this point. So again, let's look at some more properties of multiplication of matrices. So again, here it's associative actually. So A into BC will be equal to AB into C. So that is something which is quite easy, not particularly useful in a lot of places except for proofs probably, but just good to know all this stuff before proceeding. Continuing, again, we have the distributive law, which says that A cross B plus C will be equal to A cross B plus A C, and that just put in another form below. And then again, I remember I was talking about the identity matrix. So again, you see how it performs as the one of matrices. So A cross I is equal to A, or I cross A is equal to A, as you would observe. And as in the next case, the zero matrix is the zero of matrices. So A into 0 will be 0, and 0 into A will again be 0. So those are just basic properties. You need not, memorize them or, continuously keep them in mind, but just, just it's good to, just have knowledge. I mean, a very essential knowledge about the fact that these do actually exist. Continuing, however, this one below is an important property in general for matrices. That is that when you're going to take the transpose of the product of two matrices, then it's just going to be B transpose A transpose. So let's say AB the whole transpose will be B transpose A transpose. Hope you make a note of that. Just keep it in mind. Again, might not be really helpful for MATLAB in specific, because it's all these stuff that we're actually dealing over here gets dealt with in inbuilt commands and functions. But again, just good to have knowledge of miscellaneous properties. If AB is equal to AC, that does not mean B is equal to C. And that if AB is equal to 0, that does not necessarily mean that A or B is 0. So these definitely, if you want to, understand these, maybe you can try out with some examples of these. But then I hope these are practically understandable, and hopefully you would have got an intuition about how this stuff works. For now, let's go to this very important concept called inverse of a matrix, which is really, really helpful in several realms, both of computation as well as mathematics. I'm not going to give you a very technical definition over here. So how I'd put the inverse of a matrix in very simple terms is that, let's say you have a number. So let's say you have a number x. So x into 1 by x will be 1, quite obviously. So what is 1 by x? In this case, you can call that the reciprocal of x, or you may denote that as x raised to the power of -1. To be very, very technical in my definition, however, it is that number which, when I multiply my first number with gives me a product of 1. So if I multiply x with 1 by x, I'm gonna get 1. Similarly, if I multiply A with A inverse, I'm going to get the identity matrix. As I told you, identity matrix actually serves as kind of like the one of matrices. So then there have to be certain conditions for a matrix to be invertible. So those conditions really don't matter. Just understand that there do have pre-existing conditions for a matrix to be invertible. Most important of which, that first of all, the matrix should be a square matrix, and second of all, remember that this inverse is denoted by A inverse. All right, so I hope you understood that, and also understand that matrix the inverse of a matrix is unique. Okay, so inverse of a matrix, all right, this is just a technical proof that shows that the inverse of a matrix is unique, which again you'll not be needing, because of course everything is inbuilt in MATLAB, so I'm not going to cover this. But I'll certainly be uploading these slides for you in the lecture notes section, so I really do hope that you can make a note of that, or just take a look at this presentation later on. So yep, let's go ahead. So the first property that we're going to study is that if you're going to take the inverse of an inverse matrix, then you're gonna get the first matrix again. So I think that is kind of evident, right? I mean, that's what you do with normal numbers too. So let's say you have a number x, you're going to change it to 1 by x, and then you're going to do 1 by 1 by x. It gives you back x. So it's just something, it's just a very easily intuitive idea. I hope I need not explain that further. And let's say you're gonna multiply a scalar with a matrix, and then you're gonna take the inverse of the collective thing. Then it's gonna be 1 by k, where k denotes the scalar, into A inverse. So basically, it's something like you're reciprocating a matrix and the constant scalar inside the bracket. Well, the scalar just goes by scalar norms. It just becomes the reciprocal, which is 1 by k. And again, the inverse becomes A inverse becomes A inverse, as it is denoted here. At this point, I actually felt that many new learners, while coming to linear algebra particularly, might have this confusion, especially that I've explained things to you in such a way that probably the inverse might just be element wise turning everything into reciprocal. So let's say I'll go back to a matrix somewhere. So let's say I'm finding the inverse of this matrix here, 1 2 4 -3 0 7 9 1 5. Then please remember that you are not supposed to reciprocate each and every element in the matrix and then say that's the inverse. Well, that is completely wrong, and that is why the inverse of matrix is something unique. Okay, it's not something that goes by scalar norms or element wise, application norms like we saw before for addition or subtraction. It is something unique, which of course, I'll later on tell you how we find this stuff out. So yep, proceeding. Again, just some properties. Again, just as we saw for transpose here also, AB, the whole inverse will be equal to B inverse A inverse. I hope that's understandable and quite intuitive by itself. All right, so one more important part. Um, that is the determinant of a matrix. So first things first, the determinant is not a matrix. The determinant is a number, and this number can be positive or negative, but it is something like it's a unique number that denotes each matrix and corresponds to some of the unique properties of that matrix. All right. So how exactly am I going to explain the concept of matrices? So it's just that you're gonna perform a particular operation or calculation upon the element using the elements of the matrix to get this determinant. In the case of a 2 cross 2 matrix, as you can see over here, what you're doing is you're taking the sum of products of the diagonal elements. So A11 and A22 minus A12, A21 will be the determinant of this matrix. However, we have just done some calculation examples in this slide. One more thing you need to understand is that a matrix, while is denoted by these square brackets, a determinant is denoted by these parallel lines. It's just to show that you're calculating a determinant there and that it's not just a matrix over there. So yep, going for determinant of a 3 by 3 matrix. Again, as I said, you're just going to hold this element A11, and then you're going to take this square of A22, A23, A32, A33, and you're going to do that cross multiplication step. So you're going to do A22, A23 minus A23, A32, and you're just going to perform certain sums and products like that. Well, of course, if I need to demonstrate to you how to exactly take the determinant, um, I might have to do some math on the board, but I don't have a board right now. So, I'm just gonna make you understand that a determinant is a number related to a matrix. And I think that's pretty much you need to know because again, there are functions in MATLAB to make you understand how these work. So you might not be at a problem anytime. So just, understand that a determinant is a number made up of calculations from the elements. And if you at all want to learn to calculate it by hand, there's always this tutorial or several good resources for linear algebra that you might go through and learn. So yep, proceeding. Um, yep. So again, there are certain numbers related to numbers and submatrices, I'd say in this case, that are related to each and every matrix. And in this case, we're dealing with a special number called cofactor, all right? So let me explain a cofactor like this. The cofactor of any element in in a matrix is such that what you're going to be doing is that you're going to be blocking the row which contains that particular element and the column that contains that particular element. So let's say the element is A12, then you're going to be blocking the row which it has in blue and the column in purple. So you have these elements remaining, right? You're going to perform diagonal sum of products on those elements to get the minor of a matrix. So the minor of A12 is basically A21 into A33 minus A23 into A31. And of course, the cofactor is just something like, giving it a plus or minus sign based on its position in the matrix. But again, don't worry about the minors and the cofactors. They're, pretty much not necessary in detail for you. Just understand one thing. There exists a type of matrix called an adjoint matrix, where this adjoint matrix is something like it's a matrix of the cofactors of all the elements. So instead of each element, I'll be replacing each element in this matrix with its cofactor to get the adjoint of this matrix. So don't worry if you didn't understand the concept of an adjoint or minor or cofactor really clearly. Everything is pre-built in MATLAB, so you'll have no cause to worry. That being said, let's continue. Mm. All right, so this stuff is just, some calculation examples of how you calculate a determinant. This stuff is not needed for our course at this point of time. Neither is this or this or this or this. Let me see. All right. So, anyways, I'm not sure if I gave the credits for this PowerPoint presentation, but I accessed it from Stony Brook University. So credits to them for preparing this wonderful presentation. Now, if you give me a second, you might just pose any questions you have in the Discord. I'll just switch my screen over to Octave so that we can start out doing this stuff in Octave. All right. All right. So I hope you are able to. Okay. So I have a question here, I guess. Um, Okay, sounds good. Okay, guys, just gonna be before going to the programming side of this lecture, I'm gonna ask if there are any questions at this point of time. If not, I'll be proceeding with the programming part now. All right, there don't seem to be any questions, which which I assume you're clear with the concepts. Well, that's a good thing. So yeah. Um, Okay, so first of all, before going into straight up with coding and introducing how matrices and stuff are declared, I'd like to go with the concept of how matrices and vectors can be used to solve a system of equations. Okay, so solve a system of equations. So what are we going to do here? So we're going to represent a system of linear equations in terms of matrices and vectors, and then we're going to perform a very small operation upon them to get our resultant values for our variables. So how does this work? So let's just take up a system of three linear equations so I can instantiate this better. So, all right, I'll take some examples. So 3x minus 4y plus 5z. Um, yep, let's just make that a comment so that doesn't run and create some mess over here. Yep, and the next equation, let's say, is 2x plus 9y minus 10z. All right. And one more system, one more equation. Let's just say 5x plus 12y minus 3. All right, so plus 3z. All right, so these are three, let's say linear equations. Oops, I forgot to put the constants. So let me just do something. Um, Let me write this again. Is equal to 10. All right. So, yep, equal to, let's say, some number. Okay. And of course, the next one. All right, so if you're confused about what I just did right now, all I did was that I created a set of three linear equations, and we are going to solve the system of equations. We're going to find out x, y, and z without performing any algebraic, calculations or manual steps using we're just going to use the octave command to get this. So we're going to be defining um, three matrices here. I mean, to be very more specific, one matrix and two vectors here. All right, so we're going to be denoting this matrix in the form AX is equal to B, where A will be the matrix of all the coefficients, X is going to be the column vector XYZ, or the solution vector in this case, and B is going to be the constants, that is 10, 14, and 24. So I'm going to be building those matrices now. So this might also serve as a tutorial for you on how to build a matrix. So observe this step closely, all right? So first row is 3 minus 4, 5. So 3 space minus 4 space 5. And so when I have to move to the next row, what I'm going to do is just I'm going to put a semicolon here, all right? I'm going to put a semicolon, and then I'm going to type out the next row, 2 space 9 space minus 10. Also, when you're typing the elements in a certain row, you can either use spaces like I have, or you can even use commas there. MATLAB and Octave both interpret those as the same. So, not much of a cause for worry there. Um, all right, so I suppose there's an issue with the streaming of the video. Let me just check that. Um, okay, so, okay, glad to know that works. Okay, so issue being solved. Okay, yep, sounds good. So yeah, I'm continuing with the A matrix. The first row 3 minus 4 5, the second row 2 9 minus 10, and the third row of course is 5 12 and 3. So if I close the square bracket, that is our A matrix, done smooth. Um, the second thing that we're going to be needing here is the B matrix. I'm sorry, the B vector, which I'll be denoting with the coefficients. Of course, this needs to be a column vector because, as you see, I mean, from visualizing the system of equations, you see it's kind of in a column, right? It's not in rows. So 10 semicolon 14 semicolon 24. So yep, and well, that will be our B matrix. So now I need to find out the values of x, y, and z. What am I gonna do? I'm just gonna type x is equal to a backslash b, and here we go. So that is the solution to the set of equations that I just typed out. That's 4.21, 0.31, and minus 0.275 will be the solution set x, y, z. So x is 4.21, y is 0.31, and z is minus 0.275. So that is how you're going to solve a system of linear equations. And during this step, I hope I've also taught you how to declare matrices and vectors. Of course, you need to understand that they are enclosed with square brackets. And then, of course, semicolon moves to the next row, while space or comma stays on the same row. At this point of time, if you have any doubts, please let me know in the forums. All right, so sounds good. I suppose you guys have got the knack of doing it. So well, that's good. So yeah, let's I've taught you how to implement these. Let me also give you another few ways to actually declare some vectors. So I mean the first way that I obviously told you is by just manually putting all the elements inside the square brackets. Another way is just use the colon operator to give a set of values. So here's how that works. So let's say there's this random vector, um, vec1, which I want to declare, having the numbers 1 to 6. And what I'm going to do is just I'm going to use 1 colon 6, and well, my vec1 will be equal to 1 2 3 4 5 6. So that's just like a simple way of doing that. But you can also use another term over here, which is that if I'm going to give it as say 1 colon 0 0.2 colon 0 point. All right, so I have a question over here. So why do the equations need the percentage symbol in front? So well, look, so the equations here are comments. Okay, there aren't actually equations in MATLAB. They're comments. So if I'm just gonna give those bluntly as they are, I'll be getting errors because number one, I can never denote something as 5x. It has to be 5 into x. So I've just put the denoted all these as comments so that the compiler doesn't return any errors and makes the command messy for me. I hope you understood that. So anyways, moving on with what we're doing here, we're declaring vector 2. So let's say I add this intermittent 0 0.2 and proceed to 6. Then well, this will be my matrix. So what you would observe is that it's just again numbers from 1 to 6, but it's numbers with a space of 0 0.2, 1.2. So 0 0.2 is the spacing between the numbers. So I hope that's clear. So these are two ways of creating matrices that are most important and most used. However, there are certain other matrix building methods that I'm sorry, vectors you mean? Yeah, I mean, yeah, building matrices as well as vectors in this case. So let me actually show you one more thing which might actually come handy for you when you're doing stuff in the future. All right. So let's say I just click on A from my workspace column, and what I'm gonna do is I'm gonna open it in the variable editor. So you see, I needn't necessarily declare the variable, I mean all the values inside a matrix or a vector on my command. I can just make it available in my workspace. I can just come over here and then I can tweak around the values. So let's say I want to make this a 4 by 4 matrix. What I'm going to do is I'm just going to add a few elements here, just some random elements. Let's say something, yep, I'm sorry. um, So, if you are, at times lazy to tweak around, or you want a more aesthetic way of doing this part of it, changing the values of vectors, feel free to use a variable editor. I mean, these tools are always available to help, and make life easy for you. But then understand one thing, unless you have the variable, you're not going to be able to do this. So here's the hack of how to do that. So let's say I want to do some vector 3, okay? So vec3 is equal to, I'm just going to be giving plain brackets here, all right? So the variable will now be available here just as a 0 by 0 matrix. I'll click on that, I'll load my variable editor, and I'll just store the values that I need. And well, that's it. So you'll see here that now it's built the matrix for me by itself. So that's just a convenient hack. I'll be dealing with more methods, however, in your next lecture, because of course matrices and vectors is a huge topic. But for now, I'll be dealing with some other stuff. um, well, yep, at this point, I'd like to interject one more thing, that you need to be familiar with what are known as naming conventions. So what naming conventions are that, um, you always start a vector's name or variable name with lowercase and the matrix name with uppercase. So you see that the matrix, the 3 by 3 matrix, is denoted by capital A, while the vector B is denoted by small b. This is just for, the case of easy identification. When you're writing huge programs, you need to, you'll be dealing with a lot of matrices. It might not be easy to keep the sizes of everything and the reasons of everything in mind. So, it's just for the purpose of convenience that we name it. And I do suggest that you name it that way. So, yep. That being said, let's also move towards one more concept of indexing these matrices. So what I mean by indexing is that, let's say I want one particular element out of my matrix or my vector, then I should be able to just get that particular element. So how I'm going to be doing this is called indexing. All right. So to give you a better concept of indexing, I'll go to the variable editor. Consider this variable a, all right? So let's say I want to pick out 3 from this matrix. Then what I'm gonna do is I'm gonna have to address this 3. So how this 3 is addressed, it's called A11, or in other words, A within round brackets, number of row, and again within number round brackets, column number. So what I'm gonna do here is I'm just gonna type A11, and well, it's going to return me 3. So let's say I need something else for an example here. So let's say we go to the third row and we're going to take the third column. So that'll be 3, 3. What I'm going to do is I'm going to go A, 3, 3. Oops, what's that? Okay, so I think that doesn't exist there, does it? All right, so yeah. Um, so yep, that's how you index that in general. So I'll give you another example using a vector. Let's say we have vec2. Let's say need the 10th element of vec2. What I'm gonna do is vec underscore 2, 10, and it's gonna give me the value 2.8, signifying that 2.8 is the 10th value in my vector here. So yep, I hope indexing might be clear for you now. Just play around with this stuff and you should be getting used to it, not like a very difficult thing. So now let's actually proceed to some operations, all right? So here's how you do addition, okay? So addition of matrices, element-wise addition is very simple. You're just gonna do yep, A33 in the questions forums. Okay, anyways, yeah, I gave a space there. I mean, yeah. Oh, I'm sorry. At Discord, like I made a typo in the previous one. That's why I got that error. It's not, denoted as three threes. It's just 3, 3. I'm sorry for that typo. So anyway, I hope you're clear with the indexing. Anyways, now, so let me just give you a basic brief of how to do some scalar operations here. So here we go. First of all, let's deal with addition. You're just going to, let's say, let me just declare two matrices first to make things easier for us. Let's say A is equal to 1 space 2 space 3. um, I mean I'll make it a 3 by 3 matrix. That's always the best way to exemplify anything. So yep, that's our first matrix. All right, so yeah, just let me declare two matrices and let's get this quick. Two. All right, so let me go to the variable editor, and please let me know in the forum if you're not able